Hello again, everyone. Thanks for attending Analog Devices JESD204B webinar series. Again, my name is Dell Jones, and I'm the Staff Applications Engineer for ADI's high-speed converter products. So here's the schedule for the webinar series. The last 2 weeks we talked about the transport layer and the data link layer. Today we will discuss the physical layer, signal integrity, emphasis, and equalization. Next week we'll discuss deterministic latency and multi-chip synchronization. Again, we won't be covering every detail of the spec, but we should cover most of the relevant parts of it while discussing some of the implementation choices we've made along the way. Today we'll be looking at some of the JESD204B physical layer specifications and relate those to ADI's implementation choices made on our converter products. We will briefly discuss signal integrity issues associated with a multi-gigabit serial interface and relate that to the insertion loss and JESD204B IMAS specs. We will then discuss equalization and emphasis and the different architectures associated with our products. We will finish by presenting some rules of thumb regarding PCB layout. First, let's take a look at some of the JESD204B PHY specifications as they relate to our converter products. This is a brief summary of the JESD204B PHY specs, very short. JESD204B is a unidirectional serial interface. The PHY specifications are derived from the LV-OIF11G specification for serial rates from 312.5 megabits per second to 12.5 gigabits per second. There's a low swing 100 ohm differential signal suitable for current mode logic. A bit error rate of 1 times 10 to the minus 15 is expected from a compliant receiver. The spec defines the intended channel to be up to 8 inches long on FR4 material up to 6 gigabits per second. It also calls for the use of PCB material with a low dielectric constant as the serial rates move beyond 6 gigabits per second. The receiver termination on our DAC devices are designed to auto-calibrate to 50 ohms. This auto-calibration requires toggling the auto-termination control bits in the SPI register map. The location of the control bits will be the same for all DAC devices that use JESD204B. The JESD204B defines the input common mode voltage limits for both DC and AC coupled receivers. For DC coupling, a range of voltages must be supported based on the nominal termination voltage. For AC coupled devices, the limits are less restrictive. ADI DACs do not support DC coupling since all of our DAC products using the JESD204B interface are built using a small process node that support up to 12.5 gigabits per second data rates. At this process, a 1.2 volt core is used to offer low power operation. At this voltage, it would require a lot of overhead circuitry in order to support DC coupling. In addition, to date, all of the FPGA vendors require AC coupling and will continue to support AC coupling in the future. So we felt it was a low-risk decision to make to just support AC coupling. Of course, in the future, we can consider adding DC coupling support if there's demand for it. Okay, while the JESD204B spec specifically mentions the suitability of using common mode logic drivers for JESD204B transmitters, most of ADI ADCs use a voltage mode driver architecture called dynamic termination. The advantage of this architecture is that it uses 75% less power while still meeting the requirements of JESD204B. Termination is automatically controlled to maintain 50 ohms impedance, and the differential output swing is programmable. All ADI ADCs fully support both AC and DC compliance. Detailed electrical specifications on the JESD204B interface are included on each device datasheet. Now let's take a look at the signal integrity related specifications and features. In a JESD204B transmission system, data is transmitted over multi-gigabit differential data channels as depicted in this example showing multiple ADCs, each with its own multi-lane JESD204 link. At these high speeds, there is an increased sensitivity to the channel losses caused by inter-symbol interference. This is a real eye diagram plot taken from one of our test boards that show a completely closed eye. Because of this increased sensitivity, distributed circuit analysis methods for modeling the transmission line should be used since a lumped model is not adequate. This illustration shows an example of what insertion loss and return loss from a network analyzer looks like using analysis software. Inter-symbol interference, or ISI, is when the effects of a lossy transmission line cause a data symbol to spread into the symbol time slot of an adjacent symbol. The image below shows an impulse response at the end of a lossy transmission line. So the data pattern going into the channel is a 0, 1, 0, 0, 0 in this case. So in the diagram, each color represents a different bit period. All of the energy should ideally be in the green section. This is referred to as the cursor. Energy in the blue, yellow, and orange sections are caused by ISI. The time slot just prior to the impulse is referred to as the precursor. Time slots after the impulse are the first, second, and so on postcursors. De-emphasis subtracts the energy in the pre- and postcursors, so only the energy at the cursor remains, theoretically, after the signal travels through the channel. We will discuss the different emphasis techniques in later slides. The strategy for overcoming insertion loss created by ISI will depend on a few variables, but it is likely that, if compensation is needed, you will choose either emphasis on the transmit side or equalization on the receive side, but not both. There could be extreme cases where both are needed. An equalizer is generally capable of compensating for more insertion loss than emphasis, but can only compensate for postcursor ISI. Emphasis generally consumes less power than equalization. Also, depending on the emphasis architecture employed, precursor ISI can be reduced. If the emphasis is used, the data in the pipeline is known and can be manipulated to reduce the precursor ISI effect, as well as the postcursor ISI effect. We will describe this in detail in later slides. I think in most cases, it will be best to use emphasis on the transmit side of the link, and then you can enable equalization if more boost is needed beyond what the transmitter emphasis can supply. So why is understanding S parameter measurements important? Well, the JESD204B spec uses insertion loss, which is the S21 parameter, and return loss, the S11 parameter, as the primary measurement criteria to characterize the channel. Insertion loss is the ratio of the power received at the output of a channel to the power that was input to the channel. Return loss is the ratio of the power that is reflected back to the source to the power input to the channel. The pictures here show examples of return loss and insertion loss. This is real data from a network analyzer where we measured a 12-inch microstrip trace on an FR4 board that had SMA connectors on either end. Insertion loss is measured in decibels and given by the equation insertion loss equals 20 times the log of the S21 magnitude. Since the log of a value that is less than 1 is a negative value, insertion loss will always have a negative value except in the ideal case where the Vin equals Vout. In this case, the insertion loss would be 0. The JESD204B specification determines insertion loss compliance based on the mask shown here. Insertion loss should be measured at 1/2 and 3/4 of the baud rate to determine compliance to the JESD204B spec. The idea here is that if you have a compliant channel along with a compliant transmitter and receiver, then no emphasis or equalization will be needed in order to obtain a bit error rate of better than 1 × 10⁻15. Return loss is also measured in decibels and given by this equation here. Again, since the log of a value that is less than 1 is a negative value, return loss will always have a negative value. In fact, in the ideal case where the reflected power is 0, return loss would be -infinity. The JESD204B specification provides the maximum return loss specification for differential and common mode inputs given in the chart here. Don't be confused by the positive values here. Since they are defining losses for return loss and common mode return loss, the negative value is implied. This is an example of an eye pattern with the JESD204B transmitter eye mask overlaid on it for lane rates between 3.125 and 12.5 gigabits per second. For compliance testing to the transmitter eye mask, the measurement is taken at the output pin of the transmitting device. As you can see, the minimum horizontal opening is 70% of the bit period, and the minimum vertical eye opening is 360 millivolts. There's also a maximum swing voltage limit of 770 millivolts. And this is an example of an eye pattern with the JESD204B receiver eye mask overlaid on it for lane rates between 3.125 and 12.5 gigabits per second. For compliance testing to the receiver eye mask, the measurement is taken at the input pin of the receiving device. The receiving device must be able to capture a signal down to this eye opening with an error rate of better than 1 × 10⁻15. In this mask, the horizontal eye opening is 70% closed, so there's just a 30% eye opening horizontally. The minimum vertical eye opening is 110 millivolts. The receiver must be able to tolerate a maximum swing voltage of up to 1,050 millivolts. Before we talk in detail about equalization, I wanted to take a closer look at the receiver eye mask spec. TJ is the total jitter. This 70% number accounts for the total horizontal eye closure allowed by the spec. Remember, the spec is written so that if you have a compliant channel along with a compliant transmitter and receiver, then no emphasis or equalization should be needed to obtain a bit error rate of better than 1 × 10⁻15. Of the 70% total jitter, 50% can come from sinusoidal jitter and bounded high probability jitter. This means up to 20% of the total jitter can come from ISI. As we start talking about equalization and emphasis, you'll see why this is important to note. So now let's take a look at equalization. The JESD204B specification does not mandate equalization. The specification only makes mention of it as a possible means to compensate for a closed eye pattern at the receiver. It is important to understand exactly what can and cannot be compensated for when determining the appropriate equalization or emphasis strategy. Both equalization and emphasis can only compensate for the low-pass effect of the PCB channel. JESD204B defines this in terms of insertion loss versus frequency, and ISI is the result of this effect. Neither equalization nor emphasis can compensate for insertion loss deviation, return loss, or non-ISI jitter. This will be especially important to remember when considering possible trade-offs when laying out the PCB, and we'll discuss these later in the presentation. There are two basic equalization architectures, passive equalization and active equalization. As the name suggests, passive equalization uses passive components to implement a high-pass transfer function that attenuates the low-frequency signal content. This provides a relative boost to the high-frequency content. Typically, there will be some sort of amplification on the back end, depending on the capability of the sampling circuit. This method is relatively low power and is straightforward to implement. Active equalization uses active components and also implements a high-pass filter transfer function, but does this by emphasizing the high-frequency content directly. This method will consume more power. On the JESD204B receiver used on ADI DACs, one of our main design goals was to minimize power. For this reason, we have implemented a passive equalization architecture. Here is an equivalent circuit diagram illustrating the passive EQ used in our JESD204B receiver. The signal coming out of the channel and into the EQ has had its high-frequency content attenuated by the channel. The high-pass transfer function of the equalizer flattens the response. At this point, the signal passes through a limiting amplifier in order for the sampling circuit to accurately capture the samples. There are two recommended equalizer settings available for users of ADI DACs. For a relatively higher quality channel, where the insertion loss meets the JESD204B insertion loss limit spec, which is 4 dB at 1/2 the baud rate, the low power setting can be used. For applications with non-compliant insertion loss, the high EQ setting should be used. With this setting, insertion loss of up to 9 dB can be compensated for. This performance is illustrated here as an overlay to the JESD204B insertion loss limit mask. As you can see, when high EQ is enabled, a channel with much more loss can be accounted for. The 9 dB limit assumes that the channel meets the insertion loss deviation limit of 1.5 dB as specified in section 4.3.1 of the JESD204B standard. So we showed this plot to you earlier. So this one on the right is a typical plot for insertion loss. Typically, to see if a board meets the limit spec, a linear fit performed on this curve. Okay. This deviation from the linear fit is called insertion loss deviation. Insertion loss deviation is limited by the spec to be 1.5 dB. Boards with lower quality dielectric characteristics will have a higher insertion loss deviation. If insertion loss deviation is minimized, then longer traces can be accommodated. So if you can limit your insertion loss deviation to less than 1 dB or half a dB, then that can directly go into your budget for insertion loss that the equalizer can account for. All right. This slide illustrates how we characterize the performance of the equalizer. For all tests, we input a signal with the worst-case eye diagram per the JESD204B spec. You will recall from earlier slides that the minimum allowed voltage swing out of the JESD204B transmitter is 360 millivolts, and the maximum allowed non-ISI jitter is 50%. This is the signal that we input into the ISI test board. To validate our performance at 9 dB of insertion loss, we used a 31-inch FR408 test board that has an insertion loss of 11 dB. The eye diagram coming out of the channel and into the DAC test board is completely closed as shown here. At the signal source, we used the PRBS7 pattern and used the DAC's PRBS pattern checker to perform bit error rate testing to a bit error rate of 10 to the minus 15. Now that we have covered equalization, let's move on to emphasis. Depending on the technique used, emphasis can be classified as pre-emphasis or de-emphasis. In either case, the idea is to apply the inverse of the channel transfer function to the signal being sent into the channel. This is illustrated in the diagrams here. The top diagram shows an impulse as it goes into the channel, which acts as a low-pass filter. The resulting waveform out of the channel shows the ISI effect of the impulse energy being spread into adjacent bit intervals. In the bottom diagram, the same impulse passes through a high-pass filter before being sent into the low-pass channel. The theoretical result is a nice impulse coming out of the channel. Whether using pre-emphasis or de-emphasis, a high-pass effect is added to the signal before going into the channel, and the end result is a flattened frequency response. As illustrated, you can see that the difference is in the resulting gain of the resulting signal. Ideally, when using pre-emphasis, the gain is 0 dB, meaning you are amplifying the high frequency content to make up for the loss of the channel. Using de-emphasis results in a loss of amplitude since the low frequency content is being attenuated. So, an emphasis that results in increased amplitude of the high frequency content can be categorized as pre-emphasis, while an emphasis that attenuates the low frequency content is categorized as de-emphasis. One method for implementing pre-emphasis is called charge injection. Charge injection is a purely analog process where the signal is passed through a high-pass filter and the resulting signal is added onto the original signal. The resulting signal is a higher amplitude during high-frequency transitions. This is a relatively low-power solution, but is not adaptable to the lane rate. The filter must be optimized for a specific operating frequency range in order to be most effective. It should be noted that adding preemphasis when it is not necessary, as in the case with a low-loss transmission line, could result in violating the JESD204B transmitter eye mask. Not only is there a minimum vertical eye opening requirement, there is also a max voltage swing limit. If you recall from an earlier slide, that limit is 770 millivolts. So this is illustrated in two diagrams here. You see that without preemphasis, the eye diagram passes the mask limit, but with preemphasis added, the 770 millivolt limit is violated. Now, violating the limit is really not that big of a deal from the aspect of being compliant, since there's no JESD204 certification required for users implementing it. The bigger concern may be from any resulting increase in EMI. So this is the same slide I showed you before. I just wanted to put up here as a reminder about our definitions of precursor and postcursor ISI. Typically, the charge injection method of preemphasis only deals with postcursor ISI. However, if a digital implementation is employed for either preemphasis or deemphasis, precursor as well as subsequent postcursor ISI can be reduced. The basic idea is to pre-distort the waveform going into the channel in order to reduce the amount of energy that bleeds over to adjacent bit intervals. This reduces ISI. This pre-distortion of the waveform is performed by a combination of digital and analog circuitry. The timing of the application of the distortion is performed digitally, and the actual distortion is done in the analog domain. When employing deemphasis, the postcursor ISI correction is implemented by subtracting a weighted value multiplied by the impulse at a delay using a digital filter. For the first postcursor, the delay is 1-bit interval. For the second postcursor, the delay is 2-bit intervals, etc. Precursor ISI correction is done the same way, except the delay is negative. This is possible by looking ahead in the pipeline. This distortion is performed on both legs of the differential JESD204B output. Hopefully the example on the next slide will make this a little more clear. So this is a block diagram for a 3-tap deemphasis FIR filter. There's one tap to take care of the precursor ISI, and then 2 more taps to take care of postcursor ISI. For each tap, the original signal is applied, goes through the appropriate delay, and the negative tap weight is applied. This effectively inverts the signal, and it is then added back to the original signal. In this example, you can see that the precursor tap weight is -1/4. You might be able to see that. Anyway, that's just showing the amplitude of this signal here is 1/4 or -1/4 the original, which is here, and it's at a negative delay. In the first postcursor time period, which is right here, we add a signal with -1/2 that is the tap weight. So basically it's inverted and half the amplitude of the original signal. And then in the second postcursor time period, we can see the tap weight again is -1/4. So all these signals are added together, and the resulting output is a pre-distorted waveform that looks something like this. So this is an example of a 3-tap case. So if this concept is not clear, please let me know. You can send a question via email. This slide summarizes the differences between the emphasis methods that ADI uses on our JESD204B transmitters. The AD9250 uses charge injection to implement pre-emphasis. Using this method will result in a larger voltage swing at the output. Our second and third generation JESD204B transmitters use de-emphasis, which normalizes the voltage swing to the high frequency content, so it is lower. Using charge injection for pre-emphasis is not adaptable to line rate frequency, so the filter must be optimized for a certain frequency range. The de-emphasis method is adaptable to a variety of frequencies. Here are some data taken from our characterization of the AD9250. As mentioned, the AD9250 uses charge injection for pre-emphasis. This test was performed at 4.9 gigabits per second using a 20-inch ISI test board. The image on the left shows the eye diagram at the output of the test channel with the receiver eye mask overlaid onto it. You can see the eye is beginning to close and the receiver eye mask is being violated. The eye diagram on the right is taken at the end of the channel with pre-emphasis turned on. In this case, the eye opens up very nicely and there are no hits on the eye mask. Both the second and third generation JESD204B transmitter implementations use one post-cursor tap that has 8 available settings for the tap weight. In order to determine the appropriate setting for the tap weight, the user has 2 options. The insertion loss can be determined by using the PCB layout tools to extract the appropriate S parameter, and then the de-emphasis can be set appropriately. Alternately, the eye diagram can be measured at the JESD204B receiver input and the de-emphasis setting adjusted until an acceptable eye diagram is achieved. Here are some measurements taken from our second generation JESD204B transmitter that's used on one of our transceiver devices. In this case, the test board is 36 inches with a measured insertion loss of 18.2 dB. The max line rate for this version of the transmitter is 6.144 gigabits per second. Each measurement was taken at the end of the channel. With no de-emphasis applied, the eye diagram is completely closed. With a de-emphasis setting of 2, the eye is opening up, but there are still eye mask violations. At the de-emphasis settings of 4 and 6, the eye looks better and better in each case. Note how the voltage swing of the output lowers as the amount of de-emphasis increases. So the original signal was 500 millivolts, and then as the de-emphasis increased, it got down to 300 millivolts here with the de-emphasis setting of 6. So our devices that use de-emphasis allow the user to increase the voltage swing independently of the de-emphasis setting. However, in most applications, this should not be necessary. Our third generation of JESD204B transmitters also use de-emphasis. The following slide shows simulation data that compares a signal with no de-emphasis to a signal with a 3-tap de-emphasis architecture and one with a single-tap architecture. For the simulation, an 8-inch 100-ohm differential trace on FR4 was modeled and run at a line rate of 12.5 gigabits per second. The insertion loss for the modeled channel is 6 dB. Here are the eye diagram plots for the 3 cases. You can see that without de-emphasis, the eye opening is pretty small. For both the 1-tap and 3-tap cases, the eye diagram is very open, and any differences between the two are small. We've actually measured the difference in jitter here, and you can see that going from 1-tap to 3 taps resulted in about a 12% improvement in the ISI jitter. For both of our products using de-emphasis, we have chosen a single-tap architecture since the performance difference between the two is very small. Additionally, the power consumption and latency are both increased as the number of taps increase. For the converter applications using the JESD204B interface, the performance of the single-tap architecture is more than adequate. Most FPGAs that support serial interfaces will have the option to employ multiple taps since they have to support many different applications. Now that we have learned about insertion loss and how it can be compensated for, let's look at some guidelines for not only minimizing insertion loss, but also other types of losses in the channel that cannot be compensated for by the devices. Keep in mind that these are guidelines, and there may be some considerations that may be at odds with other system or board level considerations. Not expected for the user to be able to employ all these methods perfectly, but they are presented so that you may understand the potential danger areas in your PCB layout. The guidelines are presented roughly in the order of their effectiveness for maintaining good signal integrity. Of course, the most effective way to minimize insertion loss is to keep the trace lengths between the transmitter and receiver as short as possible. Also, using a PCB material with a low dielectric constant will reduce insertion loss as well as insertion loss deviation. JESD204B spec recommends a premium PCB material for lane rates above 6.25 gigabits per second or trace lengths longer than 6 inches. Having said that, we realize that most users will be using FR4 material. With proper layout and routing techniques, the use of FR4 material should be acceptable for rates up to 12.5 gigabits per second. We do recommend that the FR material have a weave with a minimum spacing between the fiber, since this will reduce insertion loss deviation. If your application requires that the transmitter and receiver be located on separate boards, impedance-controlled connectors and cables should be used. Before talking about routing, one thing we need to keep in mind is that while minimizing insertion loss is important, it is even more important to minimize return loss by minimizing the number and magnitude of impedance mismatches along the routing path. Remember, we can compensate for some amount of insertion loss, but all other losses must be managed by good layout and routing techniques. When routing the differential data pairs, we recommend using a single plane and referencing the traces to an unsegmented ground or power plane. The traces should be impedance controlled to achieve a single-ended 50 ohms to the reference plane. The routing should be coplanar and loosely coupled, and the trace width maximized. This will make controlling the impedance much easier. Tightly coupled refers to differential pairs that have on the order of 2% crosstalk or more. A typical configuration considered tightly coupled would be a 5 mil trace width with 5 mil edge-to-edge spacing, whereas loosely coupled would be more like 5 mil traces with 15 mil edge-to-edge spacing. Loosely coupled refers to pairs that have very little crosstalk. Trace widths of at least 8 mils using 1 ounce copper are recommended. If possible, matching the trace width to the pin or ball width will minimize the impedance mismatch where the trace and pin intersect. In the spirit of reducing impedance mismatches, it is critical that the differential pairs are not referenced to a segmented plane, but only an uninterrupted plane. As for the device clock and sysref traces, these should also be impedance controlled for 50 ohms to ground. There are a few things to consider when deciding to use strip line or microstrip PCB traces for differential pairs. As for insertion loss, there may be a slight advantage to using a strip line routing technique. This chart depicts examples of insertion loss for different trace lengths in FR4 PCB material. Copper weight, trace width, and dielectric thickness are characterized for 50 ohms impedance. Keep in mind that not all boards are the same, and that this is just given as a typical example. In this example, you can see that for a 20-inch PCB trace using strip line, the loss at 5 gigahertz is about 12.5 dB. If we look at the same plot using microstrip routing, the 20-inch trace has a loss of about 15 dB at 5 gigahertz. Strip-line routing also has the advantage of emitting less EMI, since the traces are buried on an internal layer where EMI is shielded by the reference planes. However, the addition of at least 2 vias per trace adds to the degree of difficulty in maintaining a controlled impedance, so impedance mismatches are likely. Using the microstrip technique is easier to implement and control the impedance as long as the component placement and routing density allow it. Given the fact that the small addition of insertion loss on the microstrip can be compensated for using emphasis or equalization, I think there are more benefits to using a microstrip technique and staying on the top layer, as long as the board layout can accommodate it and the EMI is sufficiently managed by other techniques. This will enable you to minimize the number of impedance mismatches along the transmission channel. The pin assignments for our devices are made such that routing on the top layer is possible. The FPGA JESD204B pins should likewise be assigned to make this routing feasible. If it's not feasible to use the top layer exclusively for routing the differential pairs, we do have some recommendations regarding the vias. Routing the traces on only one internal layer and the top layer using just 2 pairs of vias is best. If possible, use blind vias to eliminate the via stub effect and use micro vias to minimize the inductance of the via. This will also help in controlling the via impedance. If using standard vias, use the maximum via length in order to minimize the stub length. For example, if using an 8-layer board, use layer 7 for routing so the stub is only 1 layer long. Here you can see you route on layer 1 and layer 7. That minimizes this stub. Also, for each via pair, at least 1 pair of ground return vias should be placed adjacently in order to help maintain the impedance through the via. For AC coupling the JESD204B lanes, we recommend using a 100 nanofarad capacitor placed as close as possible to the receiver. Above 6 gigabits per second, smaller capacitance can be used. Again, if you can match the pad size for the capacitors or any terminations to the trace width, it will help minimize any impedance mismatch. For most ADI devices, the terminations are included internally, so external terminator is not necessary. All right. Well, that's it. Again, thank you very much for attending today. And if you have any questions, please send them to your local ADI representative or distributor so it can be routed appropriately. We do have a question about analog ground and digital ground planes. In general, we recommend just using a single ground plane and not splitting the ground planes in order to avoid the ground loops. I don't think it's necessary to segment. I mean, if you are going to segment it, you need to take all the appropriate measures to eliminate ground loops. The main thing, if you are using any segmented planes, as you're routing the JESD lanes across and they're referencing the planes, that whatever plane you're using for a reference needs to be unbroken and just solid, because any time there's a break in the plane underneath those traces, that's an opportunity for impedance mismatch, which that kind of loss in your lane cannot be compensated for with equalization or emphasis. So really need to be careful about minimizing reflection points or impedance mismatches. All right, so if you didn't get a chance to ask your questions today, we do want you to send those to your sales rep or your FAE so they can get those questions back to me and I can make sure they get answered. If you have any feedback regarding the content of the presentation or any other aspect of the session, we'd appreciate that as well. Our goal is to make this as useful as possible for you. All right, thank you again. And I'll talk to you again next week at the same time, and we'll be talking about deterministic latency. We'll talk to you again next week. Bye.